Let's look at a generic reaction with two reactants. Suppose we have A moles of A react with B moles of B to form products. We can write a rate expression where the rate of that reaction is equal to the change in concentration of A divided by the change in time times the number of moles of A in our balanced chemical reaction. And that rate must also be equal to the change in concentration of B divided by B, the moles of B, the coefficient we have B, divided by the change in time. But this is the rate over some period of time. It's not the instantaneous rate because we have this delta T in the bottom there. We can also write the rate law expression, which gives us the instantaneous rate at any one time, where we have rate equals the rate constant K, this is a lowercase k, times the concentration of A raised to some power m, this is the order of reaction for A, times the concentration of B raised to some power n. M and n are not necessarily A and B in the reaction. Now, these orders m and n are generally integer values between 0 and 2, so 0, 1, or 2. But they can be other values. They could be negative values, or they can be fractional values like 1.5 or 1/3, 2/3. But in this class, most of the time, m and n are going to be 1 or 2. So suppose we perform the reaction in a few trials where we change the concentration of the reactants A and B. And then we can compare the rates to determine the values of m and n. We can take a ratio between two sets of this rate law where we have rate 1 over rate 2, and rate 1 has to be equal to K times the concentration of A raised to the m and so on. So K1, concentration of A1 to the m, concentration of B1 to the n, and divide by a similar expression involving the second trial. Now, we could at this point plug in values here and solve, but let's do a little bit of algebra first. Let's combine together the K's and the A's and the B's into three separate fractions. So we now have this fraction, K1 over K2. Well, as long as we keep the temperature constant, K1 is equal to K2, and so this fraction has a value of 1. Then we have this fraction, the ratio between the concentration of A in trials 1 and 2 raised to the n. And we have a similar fraction here where we have the concentration of B for trials 1 and 2 raised to the n. And now let's go ahead and plug in some values. So let's look at trials 1 and 2. We have over here on the left, rate 1 over rate 2, so that's 10 over 20 molar per second. I'm going to leave the units off for this calculation just to keep things a little simpler. And then we have this value, which again is 1, so I'm going to ignore that. And then we have these two terms for A and B. So let's put our A term in and our B term in. So our concentration for A in trial 1 was 2, and in trial 2 was 4. And then it was, for B, the concentration was 2 for both of them. And so, again, the fraction here is 1, and the value of 1 raised to any power is still 1. So this fraction, then we can ignore, and we then have, over here, we can simplify this to 1 over 2 equals 2 over 4, simplifies to 1 over 2 raised to the m. So if 1/2 equals 1/2 to the m, that means m must be 1. So now we know that m equals 1. We do a similar thing here with trials 1 and 3, where again, now we're keeping A constant and altering B. In this case, the rate, we again are doubling the concentration of B And here the rate didn't double, it quadrupled. So in this case over here, we would have 10 over 40. The value for A here is 2 over 2. Know the value for M. I can go ahead and plug that 1 in there, but it doesn't matter because this is still 1. And over here we have 2 over 4. So now we have 1 over 4 over here. Our ratio here is still 1 to 2. And now we need to solve for n. So now n is no longer 1, but in this case n is 2. So n equal 2. So now we can rewrite our rate law expression with m replaced with a 1 and n replaced with a 2. In this case, we can say that the reaction is first order with respect to A and second order with respect to B, and then the sum of those two, so 1 plus 2, so 3, the reaction is third order overall. At that point, we can take our rate law expression and plug in any of the 3 trials and solve for K, because we have rate, we have the concentration, we have concentration of A, we have concentration of B, we have now the orders, and then we can solve for K, the rate constant. Now again, everything we've done thus far assumes that that rate constant is a constant value, which requires us to keep the temperature the same between all of our trials. But we have another equation that we can use if we do collect data over multiple trials where we are changing the temperature. We then have this equation that we derive from the Arrhenius equation. The natural log of K1 over K2 is equal to 1 over T2 minus 1 over T1 times EA over R, where again the K values here are the rate constants at temperature 1 and temperature 2. T1 and T2 are temperature 1 and temperature 2. EA is the activation energy for the reaction, and R is the value of the gas constant, which in this case we would use a value for R of 8.314 joules per mole K. Now be careful here, because often we're using joules per mole K here, but often the activation energy is going to be given to us in kilojoules per mole. And so you're going to have to do some unit conversion to get from kilojoules per mole to joules per mole or vice versa. So let's talk a little bit about safety. The hydrogen peroxide that we're going to use in this experiment is the same concentration that you can buy at the store. However, it is a strong oxidizer and an irritant, and if you spill any on yourself, wash the affected area immediately.